Alright, let's start. Hey everyone, welcome to this webinar on natural language processing. My name is Raman and I'll be your host today. A little about me. I'm a machine learning developer at DAC and I've been working on NLP for the past few months. So in this webinar, I'm going to walk you through what NLP is. We'll see what NLP is and how it's done. So we all understand that NLP is something related to processing text and it's related to artificial intelligence. In fact, we might be acquainted with a few examples of NLP, like for example, the spam classification, or something a little more complex, like machine translation, or something even more complex, like Siri or Alexa. So we do have an idea of what NLP is, but let's understand it a little better. So NLP or natural language processing comes under the field of artificial intelligence. And in AI, we are trying to make the computer smart by teaching them to understand and think. So specifically with NLP, the goal is to teach the computer to understand and interpret natural language. Now, natural language is not something specific like French or German. It's the way people communicate. So people communicate essentially through two ways. That's either text, like messages or stories, or through audio, like conversations or podcasts. So the goal of NLP is to develop programs which can automatically extract information from this text and then feed it to a computer so that it can understand better. Now there are two main components of natural language processing. One is the NLU and the other is NLG. So NLU comes under the umbrella of understanding how natural language works. So for a very simple example, if you ask Siri to write a poem for you, Siri can understand that you are asking it for a poem, and this comes under NLU. Now Siri will work on generating a poem for you. Now this part comes under natural language generation. Now virtual assistants like Siri or Google assistants are very advanced and they use the best algorithms right now in natural language processing. But it wasn't always this advanced. NLP started way back in the 1950s. And to understand NLP, we really need to go back and trace the evolution to current times. So the outline of this webinar is going to be as follows. We are going to start off with looking at how NLP worked way back in the 1950s. We are going to understand that it's based on rules, and then we are also going to look at why we shifted to machine learning based natural language processing. Along the way, we are going to do a small project in which we are going to classify the reviews from Amazon as positive or negative. So please stick around till the end because there are some bonus slides where I'll show you some cool NLP projects which you as a beginner can easily build. So let's take this very simple example. This is a review about a hotel. And now the task is to classify this review as positive. Now remember that this is a rule-based approach. So you would come up with rules like you would if you're writing a program. So the idea is to search for all these words which indicate that this review is positive. Like for example, the words here like good indicate that the review is positive. Look at this example. The number of words which indicate that the review is positive just increased. And there could be a lot more such words which you might need to look for. What about in this case? A simple word, the not here, negated the whole meaning of the sentence. So this tells us something, that words by themselves don't represent the meaning of a passage or the sentence. Only the whole sentence can convey a message. So why is that? Because a sentence has a grammatical structure associated with it. And sentences also convey meaning. Now let's start talking about them one by one. So each sentence has something known as a part of speech associated with it. Now these are the parts of speech listed down here: noun, verb, adjectives, and so on. The goal in NLP, or at least in rule-based NLPs, was to identify these part of speech, and using them we could process the text further using some more rules. So look at the sentence. The room was good. We are able to identify the part of speech of this sentence, and then in fact we are also able to identify the relationships. Now this image was plotted using a Python library called Sparsity. Do check it out if you want to get more into NLP. We can even create a more complex part of speech and relations. For example, like this. So we can say that finding the syntax or the grammar of a sentence is something which we can do using NLP and rule-based and natural language processing. Take a look at this example. It says that the dog is running. Syntactically or grammatically, this is correct. Now take a look at this example. The whale is running. So syntactically, it does make sense. But does the whole sentence as a whole convey meaning? I don't think so. So the idea of a sentence making sense is called semantics. So clearly, words don't make sense, but sentences can make sense. For a sentence to make sense, it definitely needs to have a grammatical structure or some syntax associated with it. But just because it has syntax doesn't mean it has semantics. To just sum it up, syntax refers to the grammatical structure and semantics refers to the meaning the sentence conveys. Now, together, these two things come under the branch of NLP known as syntax and semantics analysis. And these two are the cornerstone of rule-based processing. And as you saw, that it's very difficult to understand the semantics of a language or a sentence. In this case, it's a very simple sentence which says, I went to the bank. Now, in this case, the meaning of the word bank just changed. So the semantics of two sentences can be really ambiguous, and it gets difficult to write rules and exceptions for all these cases. Take a look at this third example. It says that I went to Riverview Bank, and believe me, this is actually a bank. So now things are getting out of hands. So how many rules or how many exceptions are you going to write as a programmer? So is there a more efficient way to do this? So yes, there is, and that's where we shift from rule-based processing to machine learning based processing. And the idea is that you teach the computer the language, and the computer learns to look for these rules and exceptions and write programs on its own. Now we're going to quickly stop here. If you have any questions, you can just ask them, because in the next section we're going to look at machine learning based NLP. So we have a question here. What are the long range dependencies in a language? So as I said in the previous examples, the meaning of this sentence changes because of words, the arrangement of words. So in this case, the arrangement of the word river next to the bank changes the whole meaning of the word bank. Now in case of a long range dependency, there will be some word at the extreme start of the sentence, and it might relate or imply to some other word which might be in the extreme end of a sentence. Now that's known as a long range dependency. Another simple example to look about is if you say a sentence which is, I learned dash language, and you could fill the dash with a lot of different words. You could fill it up with French or German. But if the sentence was, while I visited France, I learned dash language. Now we know that because of this long range dependency between France and language, the blank would probably be filled with French. So I hope that cleared out about long range dependencies. And in fact, we'll see how we can cover these long range dependencies later. Alright, so let's move on. So, natural language processing using machine learning. So, if you don't know what machine learning is, let me give you a very quick example. Suppose you're using something like Google Translate. You give it some text in some other language and you get your output back in a foreign language. So how does Google Translate does it? So Google Translate essentially uses a machine learning algorithm. So how a machine learning algorithm works is you give it some data, and this machine learning model or this algorithm is going to give you some output. Now you don't have to explicitly program how to get this out from the input. The machine learning algorithm can do it on its own. You just have to provide it with a lot of data of, let's say you're translating from English to French. You're going to give it a lot of English and French data, or French translation, and the machine learning algorithm is going to look at both the sides and try to draw relations and comparisons between the English and its French counterparts. To look at a even simpler example, consider this machine learning model. Now this machine learning model, or inside it as an algorithm, you're giving it 3 inputs, that's symptoms of a disease, and this machine learning algorithm or model, I'm going to refer to this as model from now on, is going to give you some output. Now how this machine learning model works is that you don't have to explicitly program. You just give it a lot of inputs about a patient whether he has disease or not and what were his symptoms. It's going to learn to identify relations between the symptoms and the disease. And as I said, the example of Google Translate, it does use machine learning, and it is an example of natural language processing. So can we build a very simple model just like this one, where we pass in inputs, which is text, and we get some output? It could be something as simple as spam classification. So how would we provide text as input here? If you had noticed in the previous example, the number of inputs I give to the model is always same. It's always the same 3 symptoms. And these symptoms, it's important to note that these symptoms are in numeric form, or it could be categorical, that is yes or no. So if it's a fever, it's going to be numeric in terms of what is the temperature. If there was cough, it's going to be categorical in terms of was there cough or no. And same for tiredness, yes or no. So can you provide text as an input to machine learning model directly? So let's just assume that we're just going to dump in these 3 words of a sentence to the machine learning model. Maybe it can work. But what if we have a different sentence with 4 words? You see, now the same model cannot be handling different number of inputs. So we have violated rule number 1. And there was another rule which said that the machine learning models need to have data given to them in numeric form. But again, text is not numeric. So before we look at how we can give this input or how this model will learn, let's try to understand how humans would learn. Let's take this example. Let's say you want to learn a new language. Let's say you're learning a Japanese. So you won't take a Japanese dictionary and memorize all the words. You would probably use a book to learn Japanese. But then again, if you really don't understand what the words in the book are, you wouldn't make any improvements. So, how do we solve this? Maybe you could build up your vocabulary using a dictionary. Maybe you could learn what the words mean. Maybe just the words which you might encounter in the book. Now, this is similar to what a machine learning algorithm would do. A machine learning algorithm obviously learns by reading a lot of books, a lot of text. It doesn't use words. Since we saw that words don't convey meaning but sentences do. But it actually helps if you build up your vocabulary by learning some words and then you use these dictionary of words as a reference. So, the approach we take to give the machine learning model or present that model with a dictionary, this approach is known as bag of words. So, a machine learning algorithm, something very advanced like Alexa, would be trained on the entire text present in Wikipedia. But before we do that, we will provide that with a vocabulary first. So, to understand what words are and what they actually mean. And the way we do it is using this approach, a bag of words. Now, we're going to see how this bag of words approach actually works. Take a look at these 4 sentences. Now, in natural language processing lingo, we call a sentence or a passage as a document. So, out of these 4 documents, we are going to build a vocabulary or a dictionary so that a machine learning algorithm can use as a reference. So, the first step is to prepare a list of all the unique words in the dataset you have. So, right now we have about 10 words, and these 10 are all the words or all the unique words present in the dataset. So, the problem we had was that our text data could not be passed on to a machine learning model because it's not numeric and the number of words in a sentence keep on changing, so the input is not constant. So, let's take the first document. It says it was the best of times, and we're going to use a bag of words approach to build a dictionary or build a set of reference so the model can use. We're going to list down the first document here, and we're going to list down all the unique words we have, and that's what's called a vocabulary. The next step is, if each of these words appear in a document, we're going to put a 1 next to it. Yes, something just like this. And if you're supposed to expand this to all the 4 documents we had, this is what it would look like. So, in a way, we are able to represent all those textual data in form of numbers, and surprisingly, all this is of constant size. So, can we now give this to a machine learning model? Well, as you can see, we can indeed give this to a machine learning model because it's numeric, it's fixed size. Now, the reason why we built a dictionary or a vocabulary is that this right now is just number. So, how would a machine learning model realize that what word it is? Well, it can go back and refer to what this word corresponds to or this number corresponds to. Before we go further, you're going to go ahead and write some code to get started with the project with whatever we learned so far. And if you have any questions, please drop them down. Alright, so please follow along with me. Go to collab.research.google.com and you'll be taken to this place where we'll write our code. So I hope you're following along. So click on this link which says GitHub, and let's just wait. So if you don't have a GitHub account, or if you don't want to follow along, it's fine. I'm going to run through this code, and I'll be explaining each part of it and how we work with text data. So please do follow along. And in case you're following with me and you're trying to run this code along with me, once you're in GitHub and you have a GitHub account, go to this place here. Go to this text box and enter my name here. That's RAMANESWARAN. So I'll just wait here for 2 minutes to see if you're all following along. So if you have reached this stage, you're going to click on this select box which says repository, and click the one which says intro to NLP, and you have this notebook that comes up. Click on it. Okay, so if you have never used Colab before, so Colab is a platform where we can run our Python code. Now these boxes you see, these are called cells in which we'll write our code, and then use this button here to run them. Now thing is, if you run a code here and you have some variables stored here, they can be accessed in the rest of the cells. Alright, so the next thing you need to do is you need to download the dataset. Now if you go to github.com and type in the name I said, so this is the repository you need to go to, and then click on this link here, which will take you to the place where the dataset is. Now what you need to do is you need to copy this dataset to your own Google Drive. Now by the way, I'll put the link to this in the chat right now. And by the way, this data is about 47 megabytes, so it might take time for you to download it. And I'll just put the link in a minute. Alright, so once you've copied that dataset to your your Google Drive, you want to import or mount your Google Drive to this Colab runtime. Essentially, you want Colab to access your files in your Google Drive. Let's wait while it boots up. And meanwhile, let me check if you have any questions. Okay, hi bro, same to you. Alright, so now we're here. You're going to click on this mount drive, and we're going to run this cell which it gave us. So now you have to go to this particular link here. It opened up right here. You need to log in. And then basically get the authorization link from there. Okay, so now we successfully mounted our drive. So if you refresh it now, you're going to see your Google Drive. Go to the place where you stored your file here. You must have copied it to some folder in Google Drive. In my case, I have a folder called Intro to NLP. And this is the dataset we have, 1429-1.csv. And we're going to get its path and paste your path right here. I already have it. This is the path to my file, and just run it. And you need to check if you actually copied the file to your Google Drive, or if the path is correct. So run this code. If you get true, then it means you're good to go. And if you need me to slow down something, please let me know in the comments. Alright, so before we start off with building a project, we need to know what these Python libraries are. So NumPy and Pandas are libraries which you use to work with data. Seaborn and Matplotlib are some libraries which you use to plot. Let's run them to import them. Alright, so now that's done. So the first thing we need to do is we need to read the dataset. We're going to use a pandas function to read the data. And yeah, we're done here. So let's take a quick peek at the dataset and see what we are dealing with. Alright, so we have a lot of information here. But what does that really want? Since we are dealing with, as I said, we're going to classify the reviews which people put for products on Amazon. We want to get the text of the review and also the rating that people gave to check if we are able to correctly classify the ratings or not. To get the names of the columns here, run the cell, and here we have reviews rating and reviews text. So what we're going to do is we are going to take particularly those two columns and then store them in another structure which we're calling it data. Now again, take a quick peek. So this data structure right now, this looks much neater than the one we had before. This is known as a data frame, and a data frame is something you would widely use if you are working with data. So you got your index on this side, your columns which contain all the values you might need to work with. So this is your attribute name, or you could call them field names, and these are the actual values. So when we are working with data, there are a lot of problems that come with it. Since all these reviews are taken from Amazon, we need to make sure that those reviews are valid. Now what I mean by valid? Valid means a review cannot be empty, obviously, and secondly, a review may not be clean. There might be emojis, there might be a lot of punctuation marks. The text may not be properly written. So we're going to handle all of this stuff right now. So first we need to check if there is any empty review. So we're going to call this function called isNull, which is going to check if there are any empty review text there. Well, we do have an empty review here. Now let's check if there are any reviews which don't have rating. So after using the isNull function on the ratings, let's see what it really gives us. Okay, so that's okay, that's fine. We have about 20 to 30 empty reviews or empty ratings. So there are a lot of things you could do to deal with this thing or deal with this type of an error. So first one would be to average all your ratings and then subtract the average everywhere. So that means these null values would get a negative review and the ratings of other reviews would be reduced. It won't really change anything about the dataset, but since we don't want to deal with all this complexity, we'll just drop them. So right now this function drop NA dropped all the rows which had null value. Alright, so the next thing we need to do is we need to reduce the number of data we're using. Essentially we want to classify the review as positive or negative, but in this case we have ratings that range from 1 all the way to 5. So let's do one thing. We'll take all the reviews which are less than or equal to 3 as negative and all the reviews which are 5 as positive. So in a way we are actually dropping all the reviews which are 4. So this is how you would combine two conditions here. So either the rating should be less than 4 or the rating should be 5. Alright, so now we have done all this. Now let's actually check what is this data we have, what is the distribution of the data. Now the distribution of data is really important because that's going to decide how you're going to judge a model, and we're going to see in a while what I mean by that. So right now I used the Seaborn library which we imported earlier to check the number of positive and negative reviews. Remember 1, 2 and 3 ratings are negative reviews and 5 is a positive review for us. Now this clearly shows that there are way too many positive reviews right now. To just quantify it, let's print the number of positive reviews or the percentage of positive reviews. Alright, so right now we have about 91% positive reviews. So what does this mean for us? Technically this dataset is an unbalanced dataset. That means that one particular class of data, in this case the positive ratings, are way too many compared to your negative reviews. So if I wrote a function, or if I randomly shuffle this thing and uniformly shuffled it in a way that each time I took a couple of reviews, 90% of them would be positive. So if you took 10 reviews out of this uniformly sampled dataset and you gave that to me, and you would ask me if this review is positive or negative, I don't even need to look at the review and I can just tell you that it's positive. And since 9 out of 10 reviews is always going to be positive, my accuracy would be 90%. But does that mean that I'm actually doing the correct job? It doesn't mean that. So one thing I got from this distribution plot is that accuracy is not a good measure for us. Alright, let's move ahead. So as I said, the data which we get is not going to be always clean. Imagine you're working with data from Twitter where people post a lot of hashtags, put a lot of emojis. You cannot build a vocabulary out of it, or you won't be able to pass it to a machine learning model. So you're going to do some pre-processing, and this is what it usually looks like. We're going to break down each sentence into words, and we're going to remove some words like is, be, and which come a lot of times and they don't actually mean anything. Thirdly, we're going to remove the punctuations like these or hash, and then lastly, we're going to convert the words to lowercase. Now, how this impact our model? Let's take a look here. This is what a sample looks like. So this is the sample of a review. This is very big, okay, and there are a lot of words in here, and I don't know if all these words really contribute to the semantics of the sentence. All we actually care about is that it is not disappointed. Remember, we are not just checking the words here, we are checking the semantics of the word. See, not disappointed, and love to use it, and like some ability. That's what we actually really care about. We don't really care about some punctuations like this or some other words, for example and I. So we're going to clean that up, and to do that we're going to import a library in Python called NLTK. It stands for Natural Language Toolkit, and we're not going to import all of them at once just because it makes it easier to teach. So we are going to first import this NLTK. It's going to download something. It's going to be over a Jiffy. So the first thing, break down the sentence into words. So we are going to import a function called a word tokenize. So essentially we want to tokenize the word, tokenize sentence into words, and we refer to words as tokens. So we have the sample here, which you saw right now. It's in the variable sample, and we're going to apply this word tokenize function as a sample, and let's see what we get. Alright, so now we have this huge list which consists of all the words. Now the reason why we broke down into words is because, as I said, we want to remove a lot of words from this. We want to remove this dot here. We want to remove words like and I. So if we process it word by word, it's going to be much easier for us. So remember the words which I said that don't contribute much to meaning. Those words are known as stop words. So again, NLTK provides us with stop words here, which we're going to download and use for ourselves. So after this process, or after this step, this variable stop words has a set of all the words which we want to remove. Now what are these words? Let's take a quick peek at them. Alright, as I said, words like but, while, below, your, they appear a lot in sentences. They're very common, but do they really mean much? Probably not. So as I said, we're going to process them word by word. To do this, we're going to use a for loop. So it's simple. We're going to loop through each word which is present in the sample. Sample was right here, this one, and we're going to check if the word is not in stop words. So if it's not a stop word, we're going to append that to the output. Okay, so now we're done. Now, did it reduce the content in our list of words? Let's check. So this was a list. It was a pretty huge list. Well, it did reduce, but not to the extent we wanted it to. But we don't generally use for loops when we are dealing with NLP, or in fact any machine learning task. We use something known as a list comprehension. So instead of working on a list with a for loop, the Pythonic way of writing it, or the better way of writing it in Python, is going to be using a list comprehension. it's very similar to a for loop. We have a forward here for each word in the sample. So if the word is not in stop words, we're going to create a list out of it. So that's what it really means. Well, if you didn't understand this list comprehension, we are probably going to deal with it again, and probably there I'll explain it again. Alright, so next up, we are going to remove the punctuation marks. So again, for that, we are going to get a list of all the punctuation marks there are. Much like the stop words, we get a list of all the punctuation marks here. So how the way we use it is, we're going to write a code something like this. So is comma in string of punctuation. Okay, and the answer is true. So that's how we're going to use it. So again, we're going to loop through each word in a sample, and the word is not present in this list of strings, we're going to make a list out of it. So let's run this code. And check what we have here. Alright, so this says that, alright, so look at this. Right now, the number of words we have in our list has considerably reduced. We don't have the commas or the full stops, and that's actually good for us. Now, lastly, very important part of syntactical analysis, which you saw earlier, is these two things, stemming and porting. Stemming and lemmatization. So before I explain what these are, let's just quickly run these and let's see what the output is. Alright, so if you saw here, the word here was disappoint, and right now the word here was disappointed, whereas the word right now, after we do something known as a stemming, it says disappoint. So what stemming actually does is, it reduces all these words such as disappointed and to its root word, that's disappoint. Now why do you do that? Because essentially both these words convey the same meaning, but if we had different words like disappointing and disappointed, it makes it much more complex to process all of them. Instead, we just retain the root word, which gives us the same meaning but also reduces complexity we have to deal with. But stemming is not always the right way, because in this example we had a word ability and that was converted to this random word which doesn't mean anything actually. So the reason this happens is that a stemmer just removes words like or suffixes or prefixes like ed and ly. So that's why we're going to do something known as lemmatization. So let's run these and let's see what we actually get. Alright, so did lemmatization do anything? Well, it didn't change disappointed, but it also didn't change our ability here. The reason why lemmatization is better and how it works is that it's just not going to remove all the prefixes and suffixes. It's actually going to check each word and then convert those words back to its root word. So if you think about it, a word like better would be converted back to good, and both the words mean the same thing, but it just reduces the complexity for our model. So if you have any questions about stemming or lemmatization, put that in the chat. I'll come back to it. So far we saw some steps. We start with tokenization, and using those tokens we removed stop words, we removed punctuation marks. We're going to do something else. We're going to check if it's an alphabet or not, and then we're actually going to check if that token is of length greater than 1, and all these are combined into a single function here, so they can apply on each of our reviews we had in a dataset. The other function is that we're going to convert the ratings to either 0 or 1. So a 0 indicates a negative review, whereas a 1 indicates a positive review. So right now this function, it takes in a rating, it checks if the rating is 5. If it is 5, the rating will be converted to 1, else rating will be converted to 0. So we're done with all the functions of how it works and how it's pre-processed. Let's actually apply the function to our main dataset. So we're going to use a very handy function which you can apply on data frame, and that's known as a map function. So what it does is it's going to take each element we have. So this is kind of a list, right? So a list of all the reviews. It's going to map each element in the list to the function and then replace whatever the output was in place of the original text. Or you could say that it just transforms each element in the list. So it's going to take a few seconds. Alright, so now our text is absolutely clean. We have removed all the null values. We then processed it and removed all the values which might hamper our model training. And now we're going to actually see what the words actually were. So we are going to generate something known as a word cloud, and all this code does is it's going to give all the text to this function word cloud, which is going to generate this plot for us. Here, this plot. So this plot indicates all the words which we had in the positive reviews. So we can see words like great, we can see words like good, easy. So a lot of people apparently bought Alexa and the Fire Stick it is. And the size of each word in this plot indicates the amount of times it occurred. So we would obviously expect words like great and good to occur a lot of times. Let's do the same for our negative words. Alright, surprisingly, I first noticed a very big good here. Well, and then what else do we see? Is there a negative word here? Okay, it says slow here. That's negative. And there are, okay, here's one, disappointed and a little bad here. Well, this data set is kind of strange because even the negative reviews have some positive words in them. But don't forget that this good could actually be not good. So the whole as I said, the whole semantics matter, not a simple word. So let's go back and check more about how we can deal with the semantics of a sentence. So let's see if you have any questions. Okay, so alright, let's move on to the presentation. So we left it at representing our text in form of numbers, and we saw that we can actually pass this in. But is it alright? Is it able to solve the main problem we had with rule-based systems, that is understanding the semantics of a system? Alright, we see that there are actually two problems, and one is that the representation is very sparse, and the other one is that it doesn't capture the meaning of it. Let's break both of them down and try to understand them. So the first step, sparsity. As I said, to build a vocabulary, to get that vector of ones and zeros we had to list all the unique words which we had in the dataset. Now, a very complex system, like as I said, maybe Google Assistant, is trained on a dataset which consists of the entire text in Wikipedia. Now, obviously, the number of unique words there, it's going to be a lot. In this example, as you can see, the number of words are about 50,000. Now, a typical sentence or even a long passage is probably about going to have about 100 words. So in this 50,000 there are about 100 ones here, and the rest are all zeros. So clearly that's a huge waste of time, and passing such a big vector to machine learning model is only going to slow the process down. But the problem which we actually need to solve is the failure to capture meaning. So these two sentences, these two words, wisdom and foolishness, they're both represented by 3 zeros and a single one. But does that convey anything to me? If it was up to me, I would give wisdom some value of positive, some maybe positive 1, and foolishness a value of negative 1, because intuitively I understand wisdom and foolishness are two opposite ends of a spectrum. Or maybe simpler example could be, I have 3 words, that's good, bad and okay. So good is positive, so I would set a value of positive 1 for it. Bad, I would give it negative 1, and okay is neutral, so I would give it a value of 0. So you can see that numbers do convey some meaning, but how do we use these vectors to represent the meanings of a word? The very simple one would be to use something known as count vectorization. It's the same as what we saw before, except there's one small modification. This one right here, it doesn't represent the fact that the word occurred or not, it actually represents the number of times it occurred in the document. So in this sentence, the time was the worst, the appears 2 times, so in this place you are putting 2 here. So this type of representation, what it's going to do is it's going to give more importance to the word that occurs more times. So in a way, these numbers actually give us a measure of importance. But there is a problem. Some very common words like the, for example, occur a lot of times in a single document. So is it really important? Actually, the doesn't really give us much meaning to our whole passage as a whole. So that's why we have an other form of representation that's known as TF-IDF. This is a little bit complex, so we're not going to look into it. But what it essentially does is, it's going to count the number of words, the number of times the word appears. That's the TF, term frequency. Now, a word like the appears a lot of times in all the documents. And again, by documents, I mean a single passage or a single file, a single document, alright? So, if a word appears a lot of times in all the documents, it means it's a common word, it doesn't add much meaning to it. So we kind of take the inverse of this document frequency. So both of these together balance the effect of the counting. So instead of counting, we do something which is known as getting the frequency of the words. But still, we haven't solved the real question. Can we encode the meaning of words in vector? So look at this sentence. I love my dash. I love my pet. What? Okay. So what would you fill that blank with? I would probably say a dog. I mean, why not? Look at this. And this. And this. Okay, I swear I'm done. Okay. But you might also argue that you can fill that with a cat. Yeah, maybe this cat. Why is that? We intuitively understand that cats and dogs are both pets. But again, for a computer, remember they're just vectors and zeros and ones. So how do we let the computer know that the cat and dog are semantically the same? Let's take a look at this particular example. This list of Pokemons, and I wanted to check which Pokemons are same. You might say that all the Pokemons of same type are same. Is it the case? Well, let's take a closer look. I have 3 Pokemons here, Coughing, Cubone and Pikachu. Let's take the first 2 Pokemons. Both the speed is very low, both the defense is very high. So in a way, these two are quite similar, even though they are different type. Now take the third Pokemon, its speed is very high, its defense is very low. So clearly, this Pokemon Pikachu is different from these two, whereas these two are similar to each other. And we did find out this similarity using numbers. And what did this number represent? It represented some of its property or its characteristics. So intuitively, we know that dogs and cats are pets because there is some property associated with it, and we also intuitively know that alligator is not a pet because they don't have the same properties as cats or dogs. Well, but a cool crocodile can be an alligator, can be a pet. Alright, what makes cats and dogs similar? Let's list down the properties. They are animals, okay, they're domesticated, fine, they're pets, they have fur, they have claws. Can we represent this numerically? So, if we had a scale of 0 to 1 and we wanted to represent these properties numerically, how to do that? For a dog, are we certain that it's an animal? Almost certain. We're certain that it's domesticated. We're certain it's a pet. We're certain it has fur. And yeah, it does have claws. Same for a cat. What about duck? Maybe it's about 60% or 0.6 it's domesticated. About 0.3 they're pets. They don't have fur. They absolutely don't have claws. So, in a way, dog and cat are similar to each other, and ducks aren't. In fact, these properties can be embedded as this vector, and all the machine learning algorithm needs to know is what these numbers correspond to. So right now, these correspond to these properties, and all the machine learning algorithm needs to do is it needs to figure out what properties and how to assign values to these properties. So how would this algorithm assign value to a property? Take a look at this example here. We're going to use something known as a neural language model. Now, that's explaining that is out of the scope of the webinar. But how it actually works is it's going to take pairs of co-occurrences or all the words which occur together in a sentence. In this example, the quick brown fox jumps over the lazy dog. If you could see here, these are all the words which occur together. So the word quick and fox and brown and fox appear together a lot of times. Let's take a look at the next example. The big brown bear is sitting in a chair. So in this example, big and bear and brown and bear occur together a lot of times. So if we give so many data to a machine learning model, the model is going to recognize or learn that a bear is brown and so is a fox, but a fox is fast, whereas a bear is just big. Let's try to understand this idea more, because representing the meaning of words or the semantics is the most important challenge of NLP. We all know that vectors, or let's say points which are similar, appear closer to each other, right? And we can cluster them. So all these points in what is this, light green, cyan, this color are similar to each other, and all these points in purple are closer to each other, whereas this point in yellow, that's not similar to these points. Now going back, even a word like dog or cat can be represented as a vector or a number. So we can plot words using something known as word embeddings. So what we saw right now, the way of representing the meaning of a word in a vector, that's known as a word embeddings. So if you think of in this way, we're essentially embedding the meaning of the word into a vector, word embeddings. So we plotted word embeddings of food. Now we have ramen and dumplings here, and spaghetti and pizza here. Now these food items, these are Asian, and they are made of rice. These are Italian, and they're made of wheat, and these are probably made of bread. I don't know, are they American? But they all have some properties which are similar to each other, and that's why the word embeddings are closer to each other. So, okay, so much talk about word embeddings, and this is one question that always pops up. So, if from a king we remove the property of a man and added the property of a woman, would we get queen? And I'm talking in terms of word embeddings or vectors which we use to represent words. Let's say our vector is very simple. It's a two-dimensional vector in form of x and y, and x represents the gender and y represents the royalness. It's similar to what we saw in cat and dog. One dimension represented the probability or the scale the property or quantify the property that it has fur or that it has claws. Similarly, this x, it quantity represents the gender and y represents the royalness. So if x is 1, then it means that the subject is a woman, and if y is 1, it means subject is royal. So king is represented by 0/1 as a vector, a man by 0, 0. Now, if you subtract these two and add the sum to here, you're going to get 1, 1, right? And 1, 1 is actually gender is woman, and royalness is it's actually royal. So a royal woman is actually a queen. So let's take a step back and try to understand what we just did here. We started with representing word in form of number, and then we moved on to embedding the properties of an object or quantifying the characteristics of any entity or subject into these vectors. And now what we did is we essentially performed mathematical operations, and somehow we were able to convey the same meaning, or in fact carry over the meaning of word through mathematical operations. Well, right now if you have any questions, feel free to ask. And by the way, we are almost nearing the end. We're just going to look at the very last step before we finally finish our model, and then we'll be looking at some cool projects. So yeah, drop down your questions. Meanwhile, I'll just start with collab. Alright, so we left our task at here. We looked at all the words which are present in our sentence. Alright, so since we saw what word embeddings are and how we can create vectors out of words, we're going to do that right now. We're going to take all the data and put that in X, and X is our variable which are going to input, which will give to a machine learning model. We're going to pre-process all the text. And by the way, we already have X and Y here. Alright, so now we're going to tokenize the words, or sorry, sentences. But right now we're not going to do the tokenization we did above. That was just for purposes shown here. To create a word embedding, we're going to use this framework called TensorFlow, and the way we tokenize it is completely different. We're going to create an object called tokenizer, and we're going to let this tokenizer build up this vocabulary we talked about. See, the crucial first step before we start building our word embeddings is that we have a dictionary for the machine learning model to reference to. So we started off, we fitted the tokenizer on the set of words we have, or set of reviews we have, and then we created a dictionary. Now let's take a look at this vocabulary or dictionary that we talked about. Alright, so these are all the words or all the unique words which you saw in the dictionary. Now, is it just these? No, actually, if you want to check the number of words in the dictionary, you're going to actually print out the length of the dictionary right now. So there are about 10,000 unique words which we found, and we built a vocabulary out of it. So we're going to tokenize it. Now, so far I've been using this word called tokenize. So what does this tokenize really mean? So this is what it looked like. So the review has been tokenized to some random numbers. Honestly, by looking at this, I don't know what the number is. But remember, the machine learning model has this dictionary to references of words. So if we use the dictionary on the same sample, we're going to get the word equivalent of it. Alright, so the first step is solved. We built a vocabulary and we converted the words into a numeric form. But we need to note that the point is that right now these sequences are not of uniform length. These just represent the words, and each sentence could have a different number of words. So what we're going to do is we're going to essentially make those sequences of size 10. So this good function from TensorFlow is going to do this. It's going to pad the sequences. What does it mean? If the review is of length greater than 10, it's going to remove everything after 10. If it's less than 10, it's going to fill those places with a pad value. Essentially, you could look at as think of it as a filler. So once we've done that, we need to split our data into a train and test set. Alright, we need to import this train test set. So just follow this code down. Alright, so what we're going to do is we're going to take about 90% of the data and we're going to use it as training. So we're going to give the data to the model so that the machine learning model can look at both sides of the data, that's the input and the output, and it's going to learn to relate the two. So if you give it a positive rating, a positive review, it's going to look at the text and it's going to look at all the words or all the group of words and try to see what part of the sentence or what semantics of sentence are possibly related to the positive rating. So let's do that. Let's break the train test setup. Alright, now before we start building our model, there's just one final thing we need to cover, and let's take a look at any questions present there. Okay, it's just a lot of my friends there. Hey guys. Okay, so back to the presentation. Alright, so the final part of building a model. So this take a look at this sentence. I learned dash language. Now since we looked at word embeddings, we know that even if fill this up with French or German, it's both going to be right, because French and German are going to be semantically similar because they are both languages and they have the same meaning. But take a look at this case. This is something I told way back early in the lecture to answer a question. So this says, while I was in France, I learned dash language. So what changed now? Definitely we can't put German here. Now why is that? That's because natural language needs to be processed sequentially. To think of a very naive example, let's suppose you're watching a movie. Now if you watch the movie at random intervals, or you watch random cuts of the movie, you wouldn't be able to understand the plot of the movie. Whereas if you watch it sequentially, the movie will make much more sense to you. Now it's something similar with natural language processing. Natural language processing only has meaning if you look at it in a sequence. That is, you start from the beginning and go through the end. So the way we are going to do this using a computer, or how a machine learning model does this, is it does something known as sequence modeling. So let's try to understand it in a very simple way. These are the five words which we have, and we need to process them sequentially. Now, what do I mean by process them sequentially? Sequentially, we are going to go in a sequence. We are going to start from the first word, go to the last word, and by process, I mean we are going to extract the information from each word and at each state. We understood that information can be encoded into vectors, so information can be represented numerically. We also saw that something as simple as an addition of these vectors can be used to transfer information. So we went from king, we subtracted man from it, and this information was added to women. So we got royalness and gender together, adding up to give us queen. So something similar. So after doing a process, you could think of process as a simple operation like addition, but actually it's going to be something little more complex in the range of multiplications, something like cosine similarity. So we're going to get a state here. Now this state is a vector, and this vector again has meaning. As I said, vectors now do have meaning, and we're going to take this vector, pass it on to the next word, and then again we're going to process this word. And again, by process I mean we're going to extract information from the word. So now we're going to do this over and over again until we reach the final step. And right now we have this vector. So what does this vector represent to us? So probably because of this word while, state 1 had information about something in some point of time, because while refers to something in some point of time, right? I refers to some person. So state 2 had information that so far this sequence is talking about some person in some point of time. So when we reach was in, this state 4 probably consists information that some person in some point of time, and that time is basically past, was present in some location. And when you process this word, we get that the location is actually a country, France. So right now state 5 has information that a person was present in France in some point of time. So if we use this information right now and we process it further, we're going to form this long distance relation between France and language. So it's kind of looking at royal and woman, which we end up getting as queen. So it's France and language, which is going to lead us to French. So and that's how a machine learning model uses these word embeddings and processes them sequentially to understand text in a way that humans do. Just for information, how a machine learning model looks like is something like this. Again, we are going through each word, and as we saw, while we're processing words using lemmatization and removing stop words, we process them word by word using a for loop. So yeah, this is right now it's a for loop. We're going to process each word, that's the word here, and we're going to get some internal state. If this was a little bit confusing, take a look at this. This is similar to the example we discussed. And this internal state is a vector which contains some meaningful information. So now we are ready to build our final model and test it out. Alright, so we're going to be using TensorFlow again to build a model. If you don't understand deep learning, it's fine, you don't need to. We're just going to look at the natural language processing part of it right now. So just run all these cells. So the two key things we learned right now: word embeddings and uh, sequence modeling. So this is the part of the model which deals with word embeddings. So we know that the input size is going to be around 10. So look at this, we are kind of passing in the information about the dictionary right here. And secondly, this is the recurrent neural network we talked about. Remember that the figure about the for loop and the internal state. So that's this, and these two things are key components to natural language processing. And in deep learning model, we usually have lots of parameters which we need to find out. Or the goal of deep learning training is to give a lot of data to your model so that it learns to find correct values for these parameters. In fact, some of these parameters associated with the embedding, here we got about 10,000 parameters. Oh, it's actually 101,000 parameters. These parameters are those values which you use in word embeddings. So all those values describing the fact that a dog has fur and claw and all these come under these parameters. That's fine if you don't understand it. Now let's start by training the model. It's going to take about 2 minutes to train it. And let's see if you have any questions. Alright, okay, so there are questions right now. Back to collab. Alright, so far we can see that we have got an accuracy of 91%. But is that actually good? As you saw that even if the model doesn't work properly, it's going to get an accuracy of 90%. So we are not actually testing the accuracy of a model. We're going to test some other parameters which are known as precision and recall. And as soon as this model finishes building, we're going to look at what precision recall are very quickly, and then get back to our presentation. Alright, so let's test this model out with our test data that we had. Okay, so to call this function accuracy score, we need to import a class, a function. It's called alright, so that's going to be alright, so let's find the accuracy score right now. So accuracy is about 91%, but then again it doesn't really matter for us. We actually want to see how the model actually performed, and with some depth to it. So what you have right now is something known as a confusion matrix. So this row here represents all the values which are actually negative reviews, and this column right here, or this row right here, represents all the positive reviews. So Whereas this column right here represents all the reviews which are model classified as negative, and this right here represents all the reviews are model classified as positive. So how are we going to use this to look at our model's performance? So the intersection here right now, 39, represents all the values which were actually negative, and the model also classified as negative, which is what the ideal situation is. Whereas this 20 here represents all the reviews which were actually positive, but then our model classified them as negative. The same case with this column here. So there were about 210 values which were actually negative, but our model classified them as positive. And this number here, that's the total number of reviews which we actually classified correctly as positive. So we're going to compute something known as recall. Now recall essentially means out of the total number of positive values, how many values were how many ratings was the model actually able to recall. So we see that we recalled about 100% of all the positive reviews. And let's take a look at the negative case. Well, our model actually performed pretty badly in case of negative ratings, because we only recalled about 15%. Now again, recall is all the values out of all the actual positive values, how many did we correctly classify as positive. Let's take a look at the precision here. Now precision is another metric which states that out of all the values which the model classified as positive, how many were actually positive. Well, in this case we see that there are about 91% of the reviews which the model classified as positive were in fact correct. Then again, we kind of fail in case of the negative review. Well, overall we did perform not so well in case of negative reviews, and the reason being, if you go back to this word embedding right here, this word cloud right here, we can see that there are no words which indicate that the review is negative. In fact, there are some words like great and good, and maybe semantically they wanted to say not good or not great, or maybe a model couldn't figure the semantics, but we did kind of fail to classify them properly. So what are the improvements that we could make? Remember, we just trained this thing for 2 minutes. One possible case is if we trained it for maybe 10 minutes, maybe our accuracy could have improved. But there's an other problem associated with it. It's called overfitting, where you just learn to work well on your training data and you fail to do that on test. And the other option was, remember these word embeddings? Now there are better word embeddings which are available out there, something which is not just 10 dimensional like in this case, which are probably 100 or 200 dimensionals, which we can use to work with word data. So what we intended to do with this model is, we want to give you a brief introduction to how we pre-process text, which you saw in case of tokenizing and stemming and even removing the stop words. And then we saw how we could break down the words into sequence, like in this case, and then how we train a very simple language model in under 2 seconds to get some decent results. Now, by the way, even if you're supposed to use the best model out there, you probably won't achieve more than 95%, and that's kind of the benchmark for this dataset. Alright, now back to the presentation. We are almost done with it, but if you want to get more into natural language processing and work on it, these are the projects that you can build very easily. You can start building chatbots, and these are 2 resources which you can use to build chatbots. One is Dialogflow from Google, and this is an open source framework which is much similar to Dialogflow. It's called Rasa. You could build a speech recognition system And there's a very simple package in Python known as speech recognition which you can use. You could do something like text summarization, where you have a huge text and then you compress them into a summary. Again, there are Python packages available which you can easily use to build into your application. There is something known as named entity recognition. Now this is quite interesting. Basically, what you do is you go through a document and then you tag each word to its entity. For example, Prince Williams is a person, navy is a color, wedding is an occasion. So remember the previous tagging we did in rule-based NLP. Now NER is somewhat like that because you're tagging each word with an entity, but it's much more advanced and much more useful. So there's a very useful library called Sparsity which you can use to build a NER. You could do something like collect data and analyze your product. So if any company launched a new product or any musician dropped a new album, you can collect the data and see what people talk about it. And you can do that using something as simple as the model we built right now, or you could use text block. Text block provides you with pre-built models, so you just need to call a function and it will give you sentiment. And to get Twitter data using Python, you're going to use something known as VPy. You can also build a Telegram bot and analyze text in chat. So to build Telegram bot, check this resource out, Python Telegram bot. And to analyze the text, you could use something like text block or build your own model like you built right now. Finally, we have something complex like information retrieval. Imagine there's a company which wants to take all its documents, let's say a law firm which takes documents and want to upload that to a cloud. You're going to manually write down each document. It's much simpler to scan all the documents and then use natural language processing to extract all the information from the document. Now that's something you should explore. Yeah, and with this we have now reached the end of the session. So if you have any doubts, you can put them down. I'll try to get back to you. And these are some resources you need to check out if you want to get into natural language processing. There's a course in Stanford called CS224N, and there's a course by Fast AI, and this course is more into programming. And by the way, the code we did right now and the presentation will be uploaded to this GitHub repository. So with this we come to the end of our session. So if we talked about, to quickly summarize what we did, we talked about what natural language processing is. We saw that it involved natural language like text and audio and to process it. We looked at how NLP used to be done, that's using rule-based processing. We saw why it was getting too out of hand. And then we moved on to machine learning based natural language processing, out of which we discussed two very important things. That's extracting meaning of a word and putting that into vector word embeddings, and that we need to process them sequentially. And this sequential data is processed through something known as internal state representations. Alright, so with this we come to the end of the webinar. So if you have any questions, please drop them down. I don't know what the NPy engine is. Can you please clarify a question if you can? So if there are any questions, we're reaching the end of the session here. So thank you guys, and please follow us on Instagram and Twitter.